Hello. Can you hear me? Yes. So yes, I was asked to say a few words, to contribute a technical talk to this conference. So I'm going to talk in 15 minutes to you about three sort of new developments at Qualcomm AI Research, which is, has an office in Amsterdam. And it's about the next generation of convolutions that we are developing there. It is blue sky research in the lab. So what is a convolution? So a convolution is basically the most fundamental and most powerful tool that we have in the machine learning toolbox. If we think of a neural network, as we can see here, every neuron in a convolutional neural network has the shape of a sequence or an image. And in order to produce, let's say, activations at the next layer of the neural network, what we need is we shift a filter with some values in it. We shift it over that image, and then we multiply the values of the filter with the underlying image, and we add them up. So that's called a multiply-accumulate operation, and it's very fundamental as an operation on a chip as well. Right? And so we can think of sort of neurons, synapses, and sort of flow of information through this neuron. So what we have done in Qualcomm AI Research is to generalize these three fundamental operations into new domains. So we can think about, can we also apply convolutions on new sort of mathematical objects? And we've done graph convolutions, and in this talk I'll briefly touch upon group convolutions to include symmetry of the data, gauge convolutions to work on curved surfaces, and finally quantum convolutions. But let's first start with another problem, which is that convolutions are actually very expensive to run on hardware. So one question that can be naturally asked is, can we design radically new hardware to reduce the power consumption of these convolutions when we run them? And here I will talk about in-memory convolutions briefly. So let's start with this. So computers and AI are going to consume an increasing amount of energy. And it's expected that in 2025, the data centers are already using up to 20% of our total energy budget. And given the speed at which AI is developing, this is expected to only increase. Now, there's something funny about neural networks that gets more and more powerful. At some point, they use so much energy that they're actually not very useful anymore. And the reason is that the revenue that you create by a neural network should outstrip the cost of actually running that neural network to provide the service. And that's already on the edge for many sort of online applications. And the brain has been very much aware of this constraint throughout the evolution, namely that it provides a service which is survive better. However, if the cost of running that brain outstrips the sort of the benefit, then it's not very useful. And for many animals, they don't have such a big brain and survive fine. But the human brain has solved this problem by being 100,000 times more energy efficient than our current hardware. So what we really need is we need more AI per joule, not necessarily more AI. And so for this, we want to be inspired by the brain. So what is wrong with our current sort of compute paradigm, which is called the von Neumann compute paradigm? In the von Neumann compute paradigm, we have two separate things, like memory and compute. So the information is stored separately in memory, and then when we need to do a computation, we have to bring that information out of memory, this is often off-chip, to the sort of logical gates where we do the sort of MAC operations or the computations. And for a neural network, this basically means that, let's say, the values of all these weights here, these synapses, are stored somewhere, and every time I do a convolution, I have to bring all these weights, to the compute, and then do the computation, which is very, very power efficient. This is the main source of power consumption. The brain does it very differently. It has its memory is distributed very close to where the compute is actually being done. And so what we are exploring at Qualcomm AI Research is what's called compute in memory, which is very much inspired by how the brain works. where we merge compute and memory to be at the same location. So here is a sort of a view, perhaps, of how that works in its most simple form. So a MAC operation is basically a matrix multiplication. So it's like you have a weight matrix, and you have some input values, and you need to multiply that matrix with the input values to get an output for the neurons at the next layer. So how can you do that analog and in memory? So what you can do is you can take the input values and present them as voltages at this crossbar design. And so now you have applied these voltages, which are proportional to these inputs. And then here we have resistors that connect the rows here with the columns. And if we now make the inverse of that resistor equal to the weight that we want to use to do the multiplication, then magically it turns out that if you read out the currents at the end of these columns here, they will actually have done, in analog, this computation of this matrix multiplication. So it's completely analog, it's not digital. And it's very energy efficient. So analog, I mean, the reason that we have gone digital is, of course, that we don't make any errors. If you do digital computation and it's very, very precise, here it's going to be very noisy. And for normal computation, that's not very good. But for a deep neural net, it's not so bad. Because in fact, when we train these deep neural nets, we actually add all sorts of noise to them in order to make them run better. So this is a good solution for power consumption. So the next thing I want to talk about is how can we do deep learning on curved manifolds and extend them to new situations. So when we analyze an image, let's say an image of a dog, and we move the dog a little bit to the left or the right, the internal representations of this neural network transform in a very natural way. They actually also shift. So internally, the transformations are very simple. Now, if you rotate the dog, as in the input as it happens here, the internal representations get all garbled up and very complicated in a normal neural net. So what we've done is we have extended the neural nets to actually also transform very nicely under these rotations. And this has very important applications, for instance, in self-driving cars, where you have to sort of look around you and sort of rotate your field of view, or in drones, where you have to look all around you, like even up and down, and it's very helpful there. In VR, where the world is actually 3D as you look at it, and on sort of curved fisheye lenses. So the next question that we want to answer then is, well, if the world is going to be increasingly 3D, with, for instance, all the depth sensors that we have, or when we do gaming, we are looking at surfaces of 3D objects. And can we do, or perhaps here when we analyze the weather patterns on the Earth, right? That's also a curved surface. So normal neural nets and convolutional neural nets actually do not work on these curved surfaces, so we have to change them. And the beauty is that the mathematics that you need in order to solve this problem is the same mathematics that is being used in the general theory of relativity invented by Einstein. And the core of the issue is that if you take a filter and you try to translate that filter to some other place, which is what you need for a convolution, it depends on the path that you are taking. And so there is no natural orientation in this space. And in order to deal with that, leaving details out of this talk, you will have to use the mathematics of general relativity to solve it. And we actually did use it to predict storms on the Earth. So it can be used, for instance, to study climate patterns. And then the third and the last topic that I wanted to discuss today is something even more blue sky and exotic, which is quantum computers. So quantum computers are actually not very far away. And one natural question you can ask, how is deep learning and how is machine learning going to benefit from the fact that we're going to have quantum computers soon? So quantum mechanics is a really bizarre theory of the world, which is very, very counterintuitive. So let me try to explain this to you by this sort of graph, where there is a source emitting light, and this is a sort of half mirror, so half of the light is going up and half of the light is going down. And then here's a reflector, so it will sort of bounce up here, and here's another half mirror, so half of it will go this way and the other half will go that way. Now, if you look at it and you don't measure anything at these positions, then due to interference, because light is a wave, you'll only find a signal here, because this path gets completely interfered away. Now, that's fine for waves, but if you're now emitting single photons, right, you would think that that photon would either take this path or take this path, right? And since these are half mirrors, you would think that you would always be in this situation. So you would go up, or you could either take this path, and then there's going to be a half probability of going here, or you're going to take this path, and you're going to be a half probability of here, and so you're going to be either hitting this or this detector with a probability of a half. Now, that's true if you will actually look at whether the photon is here or here. Now, if you don't look where the photon is, then in fact you get this interference pattern again. And this is truly weird, because it means that the photon, the single photon, when it takes one of these paths, it is aware of the other path it could have taken and still interferes with itself. Now, if you think about that, that is a weird theory of probabilities, or a weird theory of statistics. But it is the theory that nature chose, so that's actually also very interesting. And it's even classically interesting to study how would deep learning or information processing look like if we follow this weird quantum mechanics sort of theory of probability and statistics. So that's what we set out to do. And the idea is to first study it classically and see what this new world of quantum statistics gives us, with in the back of our minds the idea that we want eventually to run this on a quantum computer, which then expands its possibility manifold. So the first thing to realize is that a qubit is not like an ordinary bit. It's not like either 0 or 1. It's much more like a value that can take any possible value on a sphere. So this is a possible value for a qubit, where a classical bit can only take 1 or 0. So it's already expanded. It's a much more rich object to work with. Now, it gets even worse, or stranger, if you take 2 qubits or multiple qubits and you do what's called entangling, some kind of operation where they start to become entangled with each other. For n qubits, you will then have 2 to the n states, so that an exponentially large number of states, where that's classically not possible. And you can take any linear combination. So this sort of quantum mechanical state where the qubits are entangled is not possible classically, and therefore much richer. So we've started to implement neural networks of this kind in our classical computers, where we take our sort of input stream, we have these entanglers which act like convolutions, and then we need an operation which sort of also deletes some of this information, which we call pooling in machine learning. So we have certain operations to do the pooling. Then, when all of this entanglement gets too large, the problem is that we need to represent 2 to the n possible states. So we cannot do this in our computer. So we need to project back onto states which are classically representable in a computer. That's called a measurement. If we measure, then we get back to states that we can represent classically. And then we continue that process, and at the very end, we're doing a single measurement to determine, for instance, whether there's a cat or a dog in the image. So we found that even classically, we can get these methods to work really well, because we have this expanded space that we are working in. But it has the additional benefit that if we run this on a quantum computer, we can now run this in a much, much bigger space, and who knows what will happen then. So to summarize, convolutions are the core technology in deep learning, and it makes a lot of sense to study how we can extend them to new domains. So I've talked about that we need to make them more power efficient, and one way to do that is to be inspired by the brain and to do them in memory directly. This is a technology that's already quite practical. The other thing is that we may want to apply convolutions on 3-dimensional spaces, like the surface of the Earth. And for that, we need to generalize convolutions using sort of the mathematics of the general theory of relativity, which describes gravity. And with beautiful applications, for instance, in medical imaging, so think of the sort of surface of a heart, and you want to track what's going on with the heart. And finally, quantum computing is around the corner, and we may want to start thinking about how we can build very powerful deep learning and neural network architectures that are based on the weird statistics of quantum mechanics and that it can eventually run on quantum computers. Thank you very much.
Professor, thank you very much indeed. I should just say a correction on my part. I said convulsions instead of convolutions.
I noticed that.
You did notice. And you were very kind not to point that out, but I thought it's good to be transparent and note that. Thank you very much. Questions for Professor Max Welling, please raise your hands. You've got a gentleman over there. Do you want to come centre stage?
Sure.
And if you, we'll just get a microphone to you, if we can. Lovely, one coming up to you. Any other questions on this side as well? Raise your hands. I've just seen you at the back there. We'll come to you next. Thank you. Ah, it worked.
Let's see if it worked. Yes, it has. Thank you very much for a very interesting talk. I just wanted to, actually a couple of questions, but I'll start with the more important one. On the quantum convolutions that you were talking about, in terms of actual physical implementation, the kind of images we'll be dealing with will contain, obviously, a lot of input pixels, and therefore you will need a lot of qubits.
I can't quite hear you.
Can I what, sorry?
Standing up.
Yes, here, sure. Now can you hear me?
Yes. I think
Closer?
Yeah.
Okay, I'll shout. So the question is, for the quantum convolutions that you were mentioning in the end, we will need quite a lot of qubits in these cases. And then we're talking about the physical implementation, because to my knowledge, the best we've done until now is like, what, a couple of hundred qubits that without decoherence? So what, 50 there, well, even better. So how are we, are there like, I mean, what's the plan to address that?
I think I understood. I fill in the details if I don't. But so first of all, the field is moving super fast. So there's already companies that are talking about 1 million qubits. I mean, that's a bit of a hyperbole maybe, but you know, people are talking about it. So the other thing is it's exploratory research. So I don't necessarily care about that it has to work tomorrow. And the other thing is that our point of view was that we are actually using this as a tool to see if we can build different, you know, neural networks that can run on a classical computer. And the reason is that the statistics of quantum mechanics is just different, but it's a consistent theory of information processing. And so there is the possibility that you're now working with complex objects that are much richer than bits. Actually, you can build better classical deep learning algorithms. So that's highly speculative, and we haven't quite gone there, so we haven't quite beaten the classical algorithms, but we have only started this very recently, and it's been a huge, interesting intellectual sort of journey.
Thank you for your question. Gentleman at the back there that had his hand up, a microphone coming to you now. Thank you.
Hello, my name is Danilo, and thank you for the lecture. My question is loosely related to the question the gentleman has just asked about the quantum convolutional networks or quantum machine learning. You've mentioned that we should move towards training algorithms on site, so in memory. But if we are doing quantum machine learning, quantum computers are still too big, so that would have to happen in the cloud. So are those two directions, you know, opposite of each other in a way? Thank you.
Yeah, that's an interesting question, of course. These two things are actually very different at this point in time. So, and about in the future, I don't know. But at this point, these are different directions in which we're exploring. One is addressing the, you know, the computational power side of things, and we're trying to sort of mimic the way that the brain does computation. The other one has to do with the fact that soon we'll have quantum computers ready, and we are just interested in exploring perhaps like an exponentially more powerful system to play with and to run our algorithms on. Whether in the future these two things will interact, I don't know. I mean, our brain is not a quantum brain, as we know, so maybe it doesn't.
Thank you very much. And just time for a very quick one. Lady at the front here, thank you.
Thanks for the presentation, quite interesting. I have a question toward actually similar but also different, because especially when in convolutional neural network, now very much the movement is toward using transfer learning for example, cross-domain, yeah? Cross-domain learning. You use simulation to also apply it for 2D images. And that type of, it means then we need less and less and less data. But then in quantum computing, to actually make it work and efficient, we need more and more and more data. So how you see these two eventually meet each other?
Okay, interesting question. Thank you very much. So I don't necessarily think that quantum computers need more and more and more data. So the jury is still out on that, right? It is, in principle, a more powerful system, but it depends on how many parameters do you sort of put in that system. So you don't have to put a huge number of parameters in them. So in that sense, you know, one is just one way to do computation differently, and the other one is a statistical question of, you know, how can you use simulations to improve the learning of neural networks? And I would say this transfer learning could be applied both to classical neural networks as well as quantum neural networks.
Thank you very much, and we appreciate your time and for fielding those questions as well. Thank you very much. Professor Max Welling, thank you.
Thank you very much. Thank you.